Welcome to HydroStore's A-Case facility here in Goderich, Ontario. This is the world's first advanced compressed air energy storage facility operating commercially in the world. Now let's go take a look at it. Starting here with the transformer and the air inlet filter. The transformer is the connection point to the electricity grid. It is connected via an underground cable that goes up the road to the substation. It transforms between the distribution voltage and the voltage of electricity that's used by the compressor and turbine in the facility. Electricity is drawn from here while the A-Case system is charging, and electricity is provided back to the facility through the transformer while the facility is discharging. The air inlet filter, housed here in the blue box, is the intake point for the air. The A-Case system uses atmospheric air as its low or ground energy state. This is actually a critical feature that enables the low cost of A-Case. Most other energy storage technologies typically require storage of both the low and high energy states of their storage medium. The A-Case system does not. The filter itself prevents airborne contaminants, such as dust and pollen, from contaminating the compressors and turbines inside the A-Case system. Now let's move on to the electrical room. The electrical room houses several important subsystems for the facility. HydroStores and utility monitoring is housed here. This monitors the amount of electricity that's consumed and produced by the facility. The utility disconnects are housed over here. This is the switchgear that will shut off the motor and generator to protect it from any electrical faults that are on the grid. It will also protect the grid in case a fault occurs on the A-Case system. The PLC, or Programmable Logic Controller, is the brains of the facility. This controls the facilities and all of its functions, including when to charge, when to discharge, and how to do so. We also have a battery that will be used to shut down the facility safely in the event of a blackout, and we have smaller transformers which further step down the voltage for the use of pumps and the fans in the facility. Now let's move on to the main act, the compressor and turbine. Welcome to the compressor room. The compressor and the turbine are the two most critical pieces of equipment in the A-Case system. This is where electrical energy is injected into the air and converted back on demand. It's fair to say that the rest of the facility simply supports the operation of these two pieces of equipment. Now let's take a closer look at the compressor. The compressor is a 5-stage, integrally geared, electrical motor-driven unit. Electrical energy comes in from the grid through the transformer into a cable into the electrical motor. The motor converts that electrical energy into a spinning mechanical energy of the shaft. That shaft, in turn, spins a large central gear here in the gearbox. That gearbox distributes the power amongst several smaller gears spinning around the periphery of the central one, each one of them with several impellers off either side. Each impeller is housed in each one of these casings. There are 5 casings and 5 impellers, hence, this is a 5-stage machine. Each impeller is a highly engineered fan blade. By spinning, it draws air in from one side and forces it out the back, moving much faster. Each one of these spiral scrolls on the outside of a stage, that speed is slowed down, converting the energy into pressure and heat. The air comes from the filter that we saw earlier, first into this first stage of the compressor, where it sequentially goes into the second and third stage. At each stage, its pressure is increased as well as its temperature. By the time it exits the third stage of the compressor, it's about 9 bar in pressure and 250 degrees Celsius. 250 degrees is about broiling temperature of your standard kitchen oven. This is both the maximum that a compressor can handle, as well as about the maximum that's economically viable to store. So from here, the hot air that's not yet at the cavern pressure has to go out to the thermal storage system to have the heat stripped out of it. Once cooled, that high pressure, low temperature air goes out into the cavern to be stored underground. And now let's go take a look at the turbine and the discharging system. The turbine is a 2-stage, integrally geared unit which drives an electrical generator. Each stage has an impeller, which is a highly engineered fan blade, which is spun by the air that flows through it, providing that power through the rotors into the central gear and into the generator. When we run the discharge system, air comes up out of the storage cavern and it is cool. First goes to the high pressure heat exchanger, where it is supplied to the high pressure or first stage of the turbine here. The air spins the impeller inside that stage, depositing its thermodynamic energy. By losing its thermodynamic energy, it comes out cooler and at a lower pressure. Before it can provide the maximum amount of power possible to the second or low pressure stage, it must be reheated. So the air goes back outside to the thermal storage system, going through the low pressure heat exchanger, which injects the heat back into it, before coming out into the low pressure or second stage. From here, the air once again spins the low pressure impeller before being exhausted to the atmosphere. Both impellers are spun by the air and spin the central gear inside the gearbox before spinning the generator, which converts that mechanical spinning energy into electrical energy, which is exported through this orange cable, back through the transformer, and back out on the electricity grid. Now let's go take a look at the thermal storage system. Here we are at the thermal storage system. It consists of 4 main components: a thermal fluid, in this case a mineral oil, heat exchangers, which enable the heat transfer between the oil and the air, a cold storage tank, which stores the fluid while it's cold, and an insulated hot tank, which stores the fluid while it's hot. This thermal storage system is one of the key innovations developed by HydroStor. It enables the process to be adiabatic. This means that the heat that's developed by the compressor while the system is charging is stored and used later on. While the system is discharging, that heat is re-injected into the air to power the turbine. This contrasts with conventional case, which wastes the heat that's developed while charging and adds new heat in by burning natural gas to power the turbine. It is the adiabatic process enabled by the thermal storage system that it allows for the AK system to be completely fuel and emissions free. Now let's take a closer look. These are shell and tube heat exchangers. The front 2 units which are paired are the low pressure heat exchanger. They're paired with the low pressure compressor and the low pressure turbine stages. The back 2, which are also paired, are the high pressure heat exchanger. They're paired with the high pressure compressor and high pressure turbine stages. When the system is charging and the compressor is running, producing hot air, cold fluid is pumped from the cold tank into both the high pressure and low pressure heat exchanger. In these heat exchangers, the heat is swapped. When the air comes out, it's cold, and when the fluid comes out, it's hot. The hot fluid is mixed together and sent jointly to the hot tank, while the air goes back to the compressor or into the cavern. In the hot tank, the fluid sits in an insulated state until it's ready to be used while the system is discharging. When discharging, the thermal storage system is reversed. Hot fluid is pumped from the hot tank into the heat exchangers. Here it heats the air, providing the air with the energy that it needs to power the turbine. The reuse of the heat exchangers on both charge and discharge is a significant feature of the AK system, as it drastically reduces the complexity and cost of the system. Now let's go take a look at the discharge silencer, the final step of the process in the AK system. This is the last step of the AK's process, and where the air leaves from the low pressure stage of the turbine and re-enters the atmosphere. The silencer allows us to do this while maintaining local noise limits. Welcome to the wellhead. The air is stored in a salt cavern 400 meters below the ground here. That salt cavern was left over from a salt extraction process. It was a brine-filled cavity that HydroStor converted into service for the AK system by extracting some of that brine and replacing it with a pocket of compressed gas. It is that pocket of compressed gas HydroStor injects air into for service as part of AKs. When the air is injected into the cavity, the pressure of the cavity rises. When air is removed for the discharging process, that pressure falls. This is the wellhead. It sits atop the well, which accesses the storage cavern. The air travels through the well and through this pipe, which is then buried up to the facility, and that's how it goes between the facility and the storage cavern. So that's it. Thanks for coming along the tour of our award-winning Goderich AK's facility. If you'd like any more information about us, please visit us on our website at hydrostor.ca.